We're now going to look at different types of data files that are used in laboratory work. We'll begin with data that's output in flat file formats. There are two types, proprietary and open. We'll look at the proprietary first. There are still vendor companies shipping software that produces output in a proprietary binary file format. Opening these files and understanding their structure for automation purposes is nearly impossible without the vendor's involvement. They designed them that way. The second type is open. Open file formats are becoming more common. The scientific community is pushing for open standards so that they can use the data in an automated systems and examine the raw results. These files often come with headers. Descriptions can also be found in the documentation. Some programs allow you to format the data specifically for an output stream that you desire. This is great for automation, but poses a problem when downstream systems are expecting file in one format and someone changes it. Most vendors provide some functionality to export data that is not in a proprietary format. Most often this is in a file format that is text-based, XML or spreadsheets. Please note, the fact that you can export data doesn't mean that you can import it and retain all the characteristics of the original data. Not all metadata will be exported, and the imported data may not meet regulatory compliance requirements. Databases are also increasingly popular for the storage of instrument and experimental output. This does not mean that the data is captured in a way that is easily decipherable for automation purposes or to look at raw data sets, but it does give IT recognizable containers to maintain data and data protection. If these software packages are coming on vendor-supplied systems, it's important to check over how the system was set up. One of the biggest priorities for IT in the labs is to protect data and do so without impacting scientific workflow. Verify that the databases has a configured backup strategy. Then make sure the backup of the databases is either being pulled off the systems onto another location or the system itself is backed up after the completion of the database backup. All commercial database platforms have mechanisms to back up their databases. Often, they can be closed so that users cannot query them with third-party software. They run the gamut in terms of their sophistication. There are many variants out there from flat file databases, Oracle's, Microsoft SQL Server, and so on. Many do not include any utilities to enable database maintenance or backups. You may need to add these utilities yourself. Some databases store protocols or methods and not the data. In some cases, these can be just as important as the data itself. Applications allow you to create a backup but have no scheduling functionality. You'll have to provide that. The automation of database backups may vary or even be in need of a script. It is important not to rely on failure notifications of a backup by email, but to verify the backup size and do scheduled restores. Data protection is the #1 reason to have IT more involved in the laboratories. Lab work creates intellectual property for the company or client. This intellectual property starts its journey as datasets in discovery. The overwhelming majority of data in the labs can be discarded, but it is this discovery datasets that eventually becomes a drug or treatment that requires a traceable process all the way back to the interesting results in a discovery lab assay. Protecting data in all labs is critical for the protection of the company's intellectual property and eventual submission to the FDA for approval. Data can be found in the databases, flat files and hard drives, raw data, and proprietary datasets. Saving the data is one challenge, including getting it off of all the systems, especially the systems not on the network. But another challenge is the restoration of datasets if the FDA wants to see them. This could constitute bringing back systems that have been decommissioned and restoring the datasets into a readable form. It is essential that a good lab IT person is cognizant of archiving operations systems, supporting platforms, and the legacy versions of software as well. The hardware capable of running the software can be an issue where proprietary PCI cards and data connections are needed. This comes into play where systems get to be 10 to 15 years in storage and the software cannot be installed on any recent platform. Where there are gaps, you can hope the software vendor has these systems and test environments available to assist you, but don't gamble on them having that capability. There are informatics systems called scientific data management systems that scoop data off the instruments and instrument systems. But the configuration and implementation of these systems probably will not cover all of the systems in the labs. Due to the expensive nature of these implementations, the initial design is for extraction of data to be coalesced for research reasons and not for data protection. Finding inexpensive but reliable solutions to data backup and databases should be one of the top priorities. At some point, there will be failed hard drives or data corruption that causes a major disruption in the laboratory. Having a recent database on hand can save them months of research. When implementing a backup strategy, don't rely on the scientist to execute that strategy. It is very important to verify the backups and that the backup activity is actually occurring. The overall point here is manual versus automation. Automation is vital. Organizations of any size can have a data management strategy that depends on users doing a manual copy and paste of data. Compliance to self-backups can be poor. Data can be lost. If you calculate the cost of all manual backup solutions, automation backups would be less expensive than the best-in-class data management and disaster recovery solutions that are out there. Bottom line, scientists should focus on what they do best, science, not sitting in meetings to discuss how they should do backups of their own data. This is an IT function, not a science function. Data management and disaster recovery should be a service provided for them to make their work less tedious and more secure. Next to the cell bank, a biotech's raw data is its lifeblood. So why cut corners on disaster recovery for it? Are backup technology and cost an issue? Storage space and cost an issue? Is there enough infrastructure available? If vital data is lost or not easily available, what is the cost and the impact? These are some of the points to make when lobbying for appropriate tools. Labs could have their own managed infrastructure with their own disaster recovery technologies, run by on-site specialists who have specialized IT knowledge for the labs. This can be expensive and will be against corporate IT management policies. Is it worth it? Measure what the data is worth and how well corporate IT manages its data and its processes. Thumb drives can be used to back up data on isolated systems and to transfer the data to another location. You can also leverage external drives to copy data sets off the system to a remote device. By scheduling this activity, you can hopefully automate the work. But you will need to touch the systems periodically on a routine basis so that you can verify that the media is not full and is performing as expected. In the case of systems not on the network, you may find that these systems are regulatory controlled systems. Check the SOPs for backup activity and even disaster recovery processes. If your backup procedure does not align with the SOP, you may need to work with a lab manager and compliance group to adjust the SOP into a workable solution. Scientists shouldn't be executing an IT responsibility. It also shouldn't surprise you that a scientist isn't following the backup procedure in an SOP. Just because they are scientists working in a regulated lab doesn't mean they understand compliance better than you do. But since you are a support person to their work, it's important to realize that you need to fill the gaps technologically and for compliance to keep them on track. Configuring network data grabs can be easily automated in most cases. However, getting the data off the systems is only half the problem. You have to schedule the testing recoveries. In the operational schedule, make sure you have scheduled time to not only look to see if backups are functioning, but that you have written procedures to recover the data. Vendors can be quite helpful with recovery procedures. Integrate export and backup functionality. Be careful the export doesn't delete the local data after the export is completed. Be aware of the types of computer hardware in the labs. Some of the companion instrument systems will be supplied by vendors. the hardware might be under a support contract. If not, a stock of computer spare parts will be important. This can be challenging when the hardware starts to age. When these systems arrive from the vendor, they are configured so the software will function. If the system is designed to be put on a corporate network, they will typically supply a list of supporting software, such as antivirus systems. Keep a library of the software both in physical and electronic forms. Keep a network share where the software are well organized. You will need old versions of the software for restoration purposes from time to time, so don't delete the old versions. To keep the network share tidy, you can keep old electronic versions of software on external drives. Just protect these drives from reuse. Also keep a copy of the physical media. It can contain needed license keys, manuals that might be removed from online sources, and supporting software versions that you're unable to find on the web. The scientists might be reluctant to let you keep the media for them, but do at least get a copy of it, a copy of the license keys, and a copy of the installation procedure. This will help when scientists move, or if there's a turnover and people do not know where the media is, or if a support call is needed and they track support by license keys. Maintaining an accurate software inventory and available licenses could make the lab manager your best friend. This work is best handled by a central, lab-focused IT organization. You might see the job of tracking instruments, service contracts, warranties, preventative maintenance, etc. fall under the responsibility of a facilities organization. In life sciences, the traditional IT models are increasingly becoming not only obsolete, but harmful. This is all the more the case in biotech and pharmaceutical research and development, which produce tremendous amounts of data. Informatics are becoming ever more sophisticated and semantic. Very soon, everything is going to be electronic. Lab notebooks, LIMS, and so on. Instruments are becoming highly sophisticated. New IT support models are required. Be aware of what software is in use. Check the current version of the software. Contact the vendor or check the website to see how long the version of the application will be supported by that vendor. What are the maximum system requirements? Can you do an in-place upgrade, for example, of its operating systems or databases? If the systems cannot run on Windows XP and is running on a Windows 2000 system, there'll be 4 choices to be made. Leave it alone, take it off the network, or suggest an upgrade and migration, or create a private network protected from the corporate network if the data needs to pass from one instrument PC to another. Find out what each instrument does at a very high level. Over time, start digging in to see how the instrument fits into the workflow, what the scientists are trying to achieve, and how they use the data. Once you understand the workflow and data sets, your experience as an IT person should be able to introduce some efficiency. Even if it's as simple as scheduling copies of data from one upstream system to a downstream system, so the scientist doesn't need to manually enter data, can help them out. You could be looked on as someone they can share their struggles that they've been working with on. Document each system's care and feeding schedule. Some of the activity can be scheduled with automation tools, but some activity will need to be manual. Even if automated tools would take some of the burden, it's important to schedule time to verify these automated tasks are not only running, but also working correctly. For example, there are some backup software packages that report successes, but back up 0 bytes. That isn't helpful. When troubleshooting instrument systems, make sure to ask the scientist what the symptoms are for the issue. Just like typical general help desk issues, the user can send you in the wrong direction. Unless there is a recurring problem, don't assume the scientist's description of the symptoms is exactly related to the cause. Get screenshots. A screenshot speaks 1,000 words, especially when the vendor disputes the issue. A screenshot of an error message or the error as experienced by the user can give you a big lead on the issue. This helps to do the initial troubleshooting and information gathering, so that when you arrive to look at the issue for the first time, your chances of resolving the problem right then and there are greatly increased. Ask the user if he or she can reproduce it. If they can't, instruct them on what to document and what to look for if the event occurs again. Have them notify you as soon as it happens again. Give them the most expedient way for them to contact you. Never rush to conclusion as to what the issue is without investigating first. This gives the end user the impression that you're unsure of what you're doing, makes them nervous, and nervous scientists are not a good thing. Google can be your friend and a powerful troubleshooting tool, but you should also be aware of a wide range of information resources and where to look for information, such as a vendor website, frequently asked questions pages, knowledge bases, forums, and so on. These are your knowledge tools. Use them. Balance is very important. Don't spend hours upon hours trying to fix an issue, especially when other problems are waiting, or users need the instrument up and running in a window of time. Know when to jump on the phone and ask the vendor for help, or ask another member of the team for assistance. Remember, the goal is to get the science back in gear. Often, you won't have the luxury of time. As an individual, you can do a lot, but a team effort can always do more. Sometimes a full resolution can take time, so try to give the users a workaround on the issue until a fix can be found. The goal is to give people as much functionality as possible so that they can continue their work. This leads to creativity. It's essential to be able to come up with creative solutions to fix some problems. Don't be afraid to think outside the box. If you have doubts as to whether or not your idea may violate a policy, check it out with someone first. Verify connections. Make sure the connections are solid between the instrument and the companion system. On closed networks, verify all the network lights are blinking. Closed networks typically don't have managed switches connecting the systems, so you'll need to work both ends of the problem and try to eliminate the switch as the problem as early as possible. Check the system log files for connectivity issues. Many issues are incredibly simple. Is a PC plugged in? Is a network cable plugged in? And so on. Knowing what questions to ask right up front can save a ton of time. After working in the labs a while, learn to trust your instincts. Begin with verbal troubleshooting. Don't be shy about asking questions. This may irritate some end users who just want you to hurry up and fix it. Patiently explain that this is all very important, given the value of the instrument, their work, and data, and that you need to be detail-oriented and careful so that you can accurately diagnose the issue before changing anything. Effective interpersonal and communication skills are essential for lab work, as are investigative discovery questions. This is a skill that can't easily be taught. It takes experience, knowledge of the instrument, and the people who use it. Check disk space of the system. When system partitions fill up, they can cause all sorts of problems. Verify if the instrument isn't showing an error message on the displays. In the event where an error message is on the instrument or is relayed to the companion system, look up the error message in the manual or online self-help. If you cannot find the error message alert in any manual or support mechanism, call the vendor. Let the scientist know you've escalated the problem to the vendor, and we'll update them as soon as you have a status change. Check memory usage on the companion system. In the event that memory is oversubscribed, start shutting down other applications to temporarily free memory until time permits a deep examination of the cause. Look for recent system updates that could have changed the security settings or patches that may have affected the application's functionality. If you can find out the last time a system was used, this will help with troubleshooting. Restart the software. Check with the scientist to see if this is an option. You may find the test is actually still in progress and the validity of the real-time results have been impacted. You don't want to impact data results, so wait for the run to end before restarting the software. Check the software logs. Almost every application keeps a log file. Open up the log file and find the lines near the time of the reported issue. Look earlier in the log file for other warnings or errors that might be related to the problem. Software that interacts with the underlying system may capture the system error codes. When checking error codes, don't always assume these error codes are software specific. Look at the operating system or knowledge database as well. It will help you determine if the error message for the operating system or the database are applicable. Check antiviruses for any quarantine files. Check that no new hardware has been added. Check also that there is only one version of the software loaded on the system. Some software packages allow you to install multiple versions of the software on the same system to access legacy data, but the old versions won't run. Check the system logs. Most systems have multiple locations for logs. These logs are the overall system logs, security logs, application logs. Make sure you look through all areas in the log files. Look for issues at the time the problem was experienced, as well as before the problem. Check accounts. Software and cross-system connections require accounts to run. Verify that the accounts are active, or that the account isn't locked out. Typically, accounts have password rotation policies. Service accounts aren't always set up with non-expiring passwords. Check to see if the service is running with a service account and not a user account. If the account is a user account, a password change could cause the application to fail. Verify any account used in the process has permissions to attach to remote systems or shares. Verify the account has the local permissions to perform the expected operations. You may find that there is an automated data archiving function that never kicked off, and the expected target either doesn't exist or the account running the service doesn't have the permissions to write to the location. Check permissions. Permissions are one of those little details that can set off a future trouble ticket. Operating systems are getting more and more sensitive to security. Permissions get trickier when you have local system security settings, local system roles, and then cross-system data transfers. Learning what takes precedence in each situation is an IT skill and often needs to be tested for verification. Reboot. In the event all else fails, rebooting is your last option. When rebooting, make sure to read all the visible messages while the system is booting up. You may find memory errors causing the system to only recognize half the allotted memory, and the error you've encountered was the system leveraging bad memory. Immediately check the logs for issues before the logs fill up and the software is activated. If the software initiates as part of the startup process, remove it temporarily from the startup process so you can slow down the process and examine each step. More about rebooting. Do this sooner than later. Depending upon the instrument, for example, a universal fix for many Waters-laced PCs is a simple reboot. Why go and spend tons of time going through a whole bunch of troubleshooting when a reboot will fix it in a few minutes? Permissions. Instrument applications often need elevated permissions. Knowing how to modify permissions on an instrument PC can take some investigative work and a call to the vendor to make sure you know what the permissions are and where they should be applied. Bear in mind a typical corporate security policy does not allow users full local administrative rights on any PC. So an instrument app requires this, you need to find a workaround. This typically involves selective permission changes on specific folders and in the registry. Be sure to have the users test the changes. When working with instruments on private networks, know your networking troubleshooting skills, as they'll come in handy here. Some of the instruments have built-in DHCP servers, and some use static IPs. Know and document what these are. Some instruments use obscure addressing schemes. Troubleshooting on-site with the vendor. Many field representatives know hardware but not software or networking. Often they will look to you for help. Whenever possible, always ask end users to tell you when a vendor comes on site. This is an invaluable time to ask questions, get deeper information and understanding of the system, and document settings and configuration. In many cases, vendors come on site, configure the instrument with unique addresses, accounts, and passwords, and promptly forget these. Many feel the information is the responsibility of the users to ask about and write down. Users typically don't. Your job is to represent the user's interest and be there to get the information. Some vendors can have personalities that can be a challenge. It's your job to be professional, but be persistent until you feel you have all the information needed. If you are new to these systems, it's important to check to see how these systems are being patched. You may find these systems are set to manual and haven't been patched in years. Don't patch them when you find this. You need to check with the software vendor if the version you have will work properly after patching, and you need to coordinate this activity with the scientist who relies on the system. Make an image of the system so you have a backup plan. Instrument applications have patches too. Make an effort to stay up to date on the availability of these as much as possible. For example, when talking to the vendor during a visit, ask if there are any new software developments. As with any other patch, assess the impact of installing it and gain the specifics for the end users. New functionalities, for example, new features and what bugs it fixes. Ideally, instruments should be in their own management structure, with its own defined policies for patching and so on. For network systems, an antivirus package will be a necessary evil. Any system on the corporate network, or any network that allows foreign systems and data sources to enter, poses a threat. Antivirus protects the lab system and also the surrounding network from an infected lab system. Every major brand of antivirus allows exclusion lists. This should be able to be done by file extension or directory. This is especially helpful with scientific applications and data. These types of applications can trigger security exceptions since they mostly aren't written for enterprise usage. The data it produces could mimic strings within the known virus signature database, causing a valued data set to be quarantined and the application to stop functioning properly. Database drive applications don't have this problem as much as flat file storage. Putting exclusions for antivirus is a good proactive approach to avoiding future problems. It's also a very good way of getting to know the applications and how it generates and stores data. Scans should be scheduled for off hours when instruments would not normally be in use, for example, late Sunday nights. Keep a running list of scientific software packages in use in the labs. You should keep track not only of the name but the versions in use. Having the vendor's website, links to self-help support, support phone numbers, username password combinations to log into support contract numbers can be very helpful when problems arise. This is also helpful when you want to do some lifecycle analysis. You should try to be aware not only of the end of life of the software and platform the software is running on, but also alternative software that can be used as a replacement. Bringing a scientist or a lab manager information that their software is at the end of life in 6 months creates a problem. Bringing them a list of enhancements to new versions, the latest version that's maybe available under their software contract, and also competitive systems and what their features are. This can avoid a future problem and provide a migration path if one is needed. If you know a new instrument is coming into the labs, especially if it's well enough in advance to do some planning, you have the ability to have a big impact on the way the instrument gets set up. You can help the users do it right and guide the users to make the best IT-related choices and decisions, and thus the overall experience is made smoother and easier for them. The ideal scenario is that the users notify you well in advance of their intent to purchase a new instrument. This doesn't always happen, but in your daily work with users, you should always remind them to get in touch with you well in advance so that you can schedule, plan, and be available for them. Let them know that if they call you the day the vendor arrives to set up the instrument, you may not have the resources you need, or worse, you may not be available at all, and the setup may not go as planned. When they do let you know, make sure you get as much information as possible. What type of instrument is it? What model? Who are the vendor contacts? Did they buy it with or without a PC? When is the vendor coming to set it up? What software does it run? Where will the instrument be set up? Then verify the location and check if a network port is nearby. Make sure it is active, and if not, enable it well in advance. Users will often ask whether they should get the PC from the vendor or use a corporate PC. This can sometimes be tricky to determine. The pros and cons of using corporate PCs versus a vendor PC is that typically a corporate PC is much cheaper. Vendors mark up their PCs significantly. A corporate PC typically uses a standard software image which is readily compliant with the corporation's services, Antivirus and Center Configuration Manager, for example. A corporate PC could be supported by in-house help desk teams. However, corporate supplied PCs may not be supported by the vendor, which can be a more serious issue. Most vendors still offer support out of courtesy, but if push comes to shove, they can use the corporate supplied PC as a mechanism to deny support. Using a corporate PC may invalidate the warranty or service contracts. The corporate PC may not meet the specifications required by the vendor in terms of both operating system and hardware, and again, the vendor may use this as an out if a serious issue occurs. Some instruments must use the vendor PC due to specialized software and hardware requirements. In any event, the next step is to contact the vendor and perform an initial discovery of the instrument and software. It's a good practice to send the vendor a questionnaire that asks detailed questions about software operations, what the critical files are, their locations, directory information, etc., so we can get a better understanding of how the software works and what we need to be aware of from a support perspective. You can then organize this information and pass it along to the end users so they are aware of what is most critical for them to do in terms of data management. Once this is completed, all of this information is documented. Then you can develop an overall support strategy for the instrument, and this should be documented as well. You can then meet with the end users to map out the strategy with them, which details their role in the process. This can include what formats the data is in, what supporting files are important, such as methods, protocols, and scripts, where these files are located. For data management, create a share on the network, which is backed up every night. Define folder and file structures and naming conventions. Also, how the data should be saved, whether it's locally or directly to the network. Establish data backup and recovery strategies and schedules, and make sure everything is documented. Work with the users and make sure they notify you when the vendor plans to arrive. Send a meeting invite to the users for the date so that this is on everyone's calendar. Meet with the vendor and review all facts and questions. Have the vendor walk you through the software basics and where all the critical files are. Review licensing of the application. Licensing can vary considerably, but in most cases, users will also want the software installed on their laptops for offline analysis. Check if this is possible, and if the install differs in any way. Track license usage. Typically, the vendor will not have administrative rights, so you will need to assist the vendor in this regard in getting the PC connected to the network. It's best to wait until the vendor is done with all the configurations before adding the PC to the domain or installing antivirus software if needed. Ideally, if this can be done while the vendor is there, but it's not required. However, check again with the vendor that doing so won't disrupt anything. Verify what permissions the applications may need and adjust accordingly. Review everything with the end users and then have them test the equipment. It is very important that they test as soon as possible before they do actual experiments, in case there are any setup issues. If there are, then these can be resolved before an actual experiment gets impacted. During this time, gather together any media and documentation that came with the instrument. This includes software CDs, licensing documents, manuals, and so on. Software should be copied to the IT library and all important docs scanned and saved as well. Have a final meeting or check in with the users to make sure everything is okay and that they know how to contact you if issues arise. Follow-up is key. This course has covered a lot of ground, beginning with the description of the life science industry to your role as an IT professional, supporting, advising, and ensuring that the tools scientists need to do their work are there and working properly. As scientific work has progressed from manual efforts to a dependence on automation and computing, your role is going to be increasingly important. The underlying technologies are evolving, products are changing with new ones being introduced at a rapid rate. What started with one scientist doing everything, from planning to programming, is now a team of cooperating professionals working towards common goals. Each has a significant role. The intent of this course is to give you the basics for meeting the challenges that you face working with scientists in developing treatments for disease and their prevention. This will add an interesting dimension to your career.